Okay, you guys, we're gonna get started. We've started the video, so just like always, this will be posted. Number one, I had said earlier to the people that are already here, but you guys have done well in your free response so far, so congratulations on that. We've started grading that. Corbin and I are actually finished with our part, and a lot of people did extremely well, so we're very proud of you guys. It's good to see this final push from you guys and everybody that's kind of kept the throttle on, has been working really hard. And not died out throughout the semester. This has been a tough semester. We understand that with all of your midterms. It's been really fun for Corbin and I to get to do these reviews with you. This is our last review because we post all these online. So those of you who haven't heard this yet, it was announced in class. There won't be a final review just because that's just so hard to do with how much material is covered, especially in this class where each chapter is so much different than the last. Besides equilibrium and acid bases, which those mesh together really well, the chapters are so much different. So make sure that if you're wanting a final review, go through the videos on the channel. And like Dr. Macedoni said, look at the test you did the worst on and start there. And go through the slides, do all the practice problems on the slides. And that would be the best method to doing well on this exam. Did you have a question?
Yeah, are there reviews posted for the first couple of tests?
No, they're not posted yet. So as soon as by the first reading day, you'll have both reviews. Corbin and I just have to rewrite a little bit of material and create a video. It won't be 40 minutes long because there won't be a lot of like interactive stuff because no one will be there. It will just be Corbin and I going over how to do a couple problems. So hopefully it'll be really precise and to the point. Okay, talking about this test. This test, I know it's been a little bit daunting because it's right before finals, and also it's hard to know, like, this is kind of weird stuff. Interesting but weird and different. And a lot of it seems a little bit factual and not so much, all semester we've done equations, solving, things like that, and this one definitely doesn't feel that way. So from my personal experience with this last multiple choices, it was easier than they normally were throughout the semester. That doesn't mean it's easy. I'm just saying it was easier because the material was more factual. So it is hard to feel like you have completely mastered this material. It's hard to feel like, oh, I know everything about alloys, because it is kind of a topic where you could look that up on Google and always read something you didn't know about it. You know what I mean? So I know that, we know that can be difficult. Tonight we're going to go over the basic things. The basic things that are probably going to be the knowledge you'll need to know to be able to answer the questions. And again, a lot of it is really factual. And so we'll probably end early, stop our video, and kind of go through people's questions individually up front. And you guys can take off and go study. To start off, let's talk a little bit about how these metals bond. We're going to go through the necessary skills list because those of you who have seen it, it's very small. Let's go through a little bit like how do metals bond? Or there's two models specifically to make this a better discussion. There are two. Can anybody name one of the two models that we need to talk about? Right here in the front.
Electron C model.
You said the electron C model, correct? And what's the other one, Jordan?
Molecular orbital.
The molecular orbital model. Okay, perfect. Those are the two models we need to talk about. So let's talk about the first one, electron C model. So that means exactly like the name says, electron C, a sea of electrons. So when I have a metal and I have all these different atoms, they're somehow bonded together, right? When I have these metals, they're not all a bunch of ions, right? I literally have a chunk of metal. And that's a ton of atoms bonded together. And one model to describe that bonding is with the C theory, meaning we have all of these nucleuses, or nuclei, right, close together, and then a sea of electrons that sort of swim throughout, right? And that sea helps there to be like a Coulombic attraction between the electrons and the positively charged nuclei, and that holds the metal together. And this model specifically said, this probably being the most important part of the model, it specifically says that the more electrons we dump into it, or the greater our C becomes, the stronger those bonds become, right? There is a greater Coulombic attraction and a greater force to hold those together. So that model says, as I increase across the periodic table and I continue to gain valence electrons, I should, in theory, of this theory, become stronger in my bonds. Now, who knows if that is 100% true, that theory? Who can disprove or prove it? Again, you brought it up. What's your answer?
So it's not completely true because once you get to group 6B, the melting points start to decrease.
Exactly. So he said once we get to group 6b, we actually start to decrease in the strength of our bonds between our metal. So the electron C model is only good, it's partly true, right? That is true in terms of talking about conductivity and this moving of electrons. That explains it pretty well, but it does not explain the true nature of what we see when we do these experiments. And what helps to further explain these boiling point trends, as we see the boiling point should, as we look at the periodic table, continue to rise, right? As I go clear to the right, the boiling point of those metals should just get higher and higher because their bonds are stronger. But he said, actually when we get to 6b, we start to decline and come back down. And that is explained by the molecular orbital theory. And that's what we need to talk about here, drawn on the board. So, again, the electron C model is exactly what we just talked about, the sea of electrons. It is somewhat true. It helps explain conductivity. But the molecular orbital model or theory is the best one. It explains more and more in depth of why certain things are happening. So this is the one I've drawn on the board because this is the one that can be hard to visualize or understand the diagram. So we're going to go through the diagram really quickly and it'll answer a couple questions of, why does this happen and what's going on. So number one, we got to understand simple things from Chem 105. So I'm going to breeze through some of those things and kind of get to this the meat and cheese of what this means. First of all, there are different types of orbitals, right? You guys know that. There's S, there's P, there's D, there's F. Right now we're going to talk specifically, and in our class we've only done examples with the S orbitals and molecular orbital theory, so that's all I'm going to talk about. So if you have questions pertaining to things a little more advanced than that, that's more of an organic chemistry question, and we would love to talk to you about it, just not on the video right now. So just come up after and we'll talk about that. But let's look at this. So any of these metals, right, all of these S orbitals line up in those two columns, right? We have our S orbitals right there. 1, 2, 3, 4, all the way down to 7 that we see on this periodic table. So when we bond a metal, and my example is lithium, like in his slide, right? We have lithium 2. Basically, we have these two lithiums that are bonded together, okay? Now, they're bonded, so we know that it worked. Like, it's happening. This isn't a fake thing. This is somehow working, and we're going to describe how is it that these two are able to come together. Well, we got to look at each one individually. I know that one of my lithiums, I guess I can put one of the lithiums here, and the other one over here, right? One of them brings one set of 1s orbitals. Can you guys see that? If I just look at one lithium, I know that lithium is element 3, right? So it has 1, 2, and all the way to 3. So it has the first end level, or S1, and it has an electron in S2, right? You guys see that? So it brings an orbital, S1. Now you guys have to remember what the S orbitals look like. And they're literally just these donut-shaped circular orbitals. Not like the P orbital, it looks like the dumbbell, right? But just the S-shaped orbital. So this orbital, right, we bring two of them. The S1 is tightly packed closer to the nucleus. The S2 is just a little bit spaced out, but they're shaped the same. So when we ever try to combine two types of orbitals, whether it be an S with an S, right? So an S orbital from one atom and the S orbital from a neighboring atom try to come together to bond, we get two things that can happen. Either they will bond and morph together to form a new orbit that looks different, right? It literally has a little bit different shape, or they will not bond, right? And they will repel each other. So when they bond, we call that our bonding orbital. That one's pretty basic, right? When these two S orbitals from neighboring atoms come together and morph together, we get this sigma bond. A sigma bonding is what we call it. So what that looks like, so the S1 orbital of one of the lithiums with the S1 orbital of the other lithium can come together, right? They morph together to form this. Lower in energy, and it's bonded together. Okay, so what we'll notice, these two dots are the two nuclei. And there literally is electron density right in between the two nuclei, as we see. So they are literally being pulled together, or they're bonding with each other, right? That's causing this molecule to literally take place, or to bond. So that's what's going on here, right? But like I said, there's always two options. If I can bond, I can also anti-bond. So we call these bondings, this is sigma bonding. We call these anti-bondings, which looks like this, a sigma star. So the star means anti. That means there is no, if you notice, in between the two nuclei, there isn't much electron density. In fact, there's really none that are causing them to be pulled together. So it's actually causing them to separate. So this is the sigma star, or the anti-bond, right? So this takes care of my 1s orbital, right? Now let's look at my 2s. It's going to look the exact same. Okay? I combine two of the s's. When I do that, I get a sigma bonding. and then another sigma anti. So for every combination I make, I get a bonding and I get an anti. So to understand whether or not this molecule is what we would deem a valid molecule, like it exists like this, we got to look at how many electrons does both of these lithium atoms bring together when they come to bond. How many electrons is that? So we know that how many electrons can fit in each orbital, you guys? 2, right. So how many does each lithium bring? Who can look at the periodic table and just count that? It brings 3. So how many total do I need to add into this whole system? 6. Okay. So we start off 1, 2, 3, 4, 5, 6. So what did we notice here? I put 2 electrons in a bonding orbital, so I gave power to this type of bond to put them together. But then I gave 2 electrons into an anti-bonding orbital, so I gave power to a bond like this. So as of right now, am I bonded, really? No, I'm not bonded. I did first, and then I canceled myself out. But then I have 2 more in a bonding, so I'm a valid bond here. This is an important thing to understand. So I do have electrons, more electrons in a bonding type orbital than I do an anti-bonding orbital. So I'm able to stick together. So why does the molecular orbital theory then explain why we have those boiling point changes that the electron C model does not? Well, what happens if I had some other type of element that had tons of electrons, and I had a huge column here of all these different orbitals I've drawn, and I'm just stacking in electrons? What happens is I continue to fill more and more anti-bonding orbitals. Even though I still am feeling bonding, I'm feeling more and more anti-bonding orbitals. What's happening there? I'm getting weaker, right? I really am getting weaker. The more and more I keep feeling anti-bonding orbitals. Even though I'm still able to bond because I have more bonding than anti-bonding, I'm still feeling a lot of anti-bonding. That weakens the bonds between the molecules, right? And so what happens is my boiling point starts to decrease. It doesn't take as much energy anymore to disrupt me or break it up. Okay, so that's the explanation behind why these boiling point trends are as they are, and what we actually see they are in experiments. The molecular orbital theory explains that, because more anti-bonding orbitals are being filled. So to quickly test our theory here, He2, is this a valid molecule? Has anyone seen this? Helium, right? A diatomic molecule of helium, we haven't seen that. And we just want to say, well, this is why we haven't seen that. Helium brings what orbital together?
2s.
The 1s orbital, and it's just one. Is it just the 1s? Yes, it's just the 1s. Like the 1s of one of them and the 1s of the other, right? So here's one helium, here's the other, right? Now I have 2 chances. I'm going to make the bonding, right? The bonding's going to look like this, and I'm going to make the anti-bonding, right? And that's going to look like this, okay? So let's just fill electrons. We'll call this our sigma, or this is going to be our sigma star. So let's fill electrons. How many are we bringing with one helium atom? Brings how many? 2. So in total we have 4, right? So we have 1, 2, 3, 4. So you'll notice, at first I bonded, but I canceled myself out with an anti-bond, so they do not stick together, right? So that is why we don't see a diatomic helium. So the molecular orbital theory explains that as well. That's all you need to know about the MO theory. Be able to understand the diagram, maybe be able to draw one or choose the correct one, judged off the number of electrons, okay?
Do you think we'll need to learn the pi or the p orbitals or no?
No, I don't think you'll need to know the p orbitals. Yeah, but we can talk about it as soon as the video is done, if you'd like to know about it. Yeah?
It might be similar to that, but I remember talking about at least Wood's class, we talked about certain molecules that have like a different molecular orbital theory. Should we know those ones? I think like nitrogen, SH weird, switched around. Do we need to know those specifics?
No. He hasn't talked about that or made that a point that was important. But rather, what he's trying to get you to understand is we're talking about solids, and this whole chapter has been kind of about how solids work and the different types of solids. And the molecular orbital theory just is explaining the boiling point trend, and I just wanted to give you a little dab into that again. But this theory is something you will not leave behind. It will stick with you. This theory answers so many questions in chemistry, it's unbelievable. So if you can get this down, you'll solve a lot of problems in your chemistry career in the future, understanding how this works, okay?
Alright, so switching gears, we're going to start talking about conductivity and semiconductors and all that. The first thing I want to talk about, whenever we talk about conductivity, what we're referring to is electrons being able to move around, right? Our electrons can flow within our metal or semiconductor when we talk about it in these cases. So the easiest way to understand this theory is when we just look at a metal itself. What you see with these semiconductors and insulators is that these will have an energy gap, while a metal has no energy gap between the valence band and the conductive band. So what that means is we have this big empty space up here with no energy gap. So these electrons down here, they can just flow, right? Those can fly up and down and back and all over the place. And that's why our metals conduct electricity really well. Next, we need to talk about semiconductors. A semiconductor will conduct electricity not as good as a metal, not as good as a conductor, and not as bad as an insulator. They're kind of right in between. And there's two types of semiconductors that you guys need to know. The first one is an elemental. And what an elemental semiconductor means is that each atom brings 4 electrons to the table. So we look at our group 4A column on the periodic table. We have silicon, beryllium, and tin. All of those will each bring 4 valence electrons. So when we stick 2 silicons next to each other, they bring 4 each to make a full octet. And that's what we're looking for with semiconductors. They have a full octet of 8 electrons. So the other type, this brings us to compound semiconductors. And that is typically with your group 3A, a group 3A element, and a group 5A element. So for example, gallium arsenide would be a good semiconductor. That would be a compound semiconductor because gallium would bring 3 valence electrons, arsenic would bring 5, we have 8 for full octet. And what we see here with how we illustrate these semiconductors is that full octet is a full valence band right here. We have a full valence band and an empty conductive band. Does anyone have any questions on this, just right here, this metals and semiconductors? Okay. So then an insulator is pretty easy to understand. The energy gap is so big in an insulator. These are like our rubbers and plastics, things that don't conduct electricity at all. The reason is because when we add a flow to here, we can never, we just can't promote the electrons into the conductive band, and insulators, they will never conduct electricity. So this is the worst conductor, medium, best conductor. Good? Yeah.
Are we gonna have to know the difference between chemical and physical properties of semiconductors?
What do you mean?
Does a semiconductor have more physical properties of a metal, or I don't know?
No, I don't think you'll have to know specifically that. I think the main thing that you'll have to know is they conduct electricity not as good as a metal, not as bad as an insulator. They're right in between. And you'll see when we do start doing some doping, we can actually make semiconductors start conducting electricity pretty well. Yeah?
Do we need to know / is there a formula for determining the band gap size and stuff?
No, there's no formula or anything like that. Yeah.
What about N-type and P-type?
We're gonna talk about that next. You read my mind. Yeah. Yeah. Okay. So yeah, Drew.
So with the elemental and compound, what were the groups that were in the elemental and compound?
The elemental is going to be your group 4A. So any element that has 4 valence electrons is going to be elemental. And then your compounds are going to be typically a group 3A element and a group 5A element. To make 8 total. That's what you're looking for with semiconductors. So, like someone brought up, there's different things we can do to semiconductors to help them start conducting electricity really well. And so I would be really familiar with these, and you guys should know by now that this is considered the valence band. What the valence band is, it's our filled molecular orbitals. And the conductive band, when it's empty, is the empty antibonding orbitals. So an intrinsic semiconductor is just like our standard compound or elemental semiconductor with 8 valence electrons. That's just intrinsic. This is just our standard semiconductor. What we can start doing is called doping these semiconductors so they will actually start conducting electricity really well. And there's 2 ways we can do that. The first way is called an N-type semiconductor. And what that is we put extra electrons in. Okay? So if I put an extra electron in, if I have a full valence band, the only place those electrons can go is up into the conductive band. And now when those electrons are in the conductive band, they've got a lot of empty space up here. They can just go move around and conduct electricity really well. So to illustrate this, just so you guys can understand conceptually how this works, I want to just use this little model right here so you can see exactly what's happening in the element. It's really hard sometimes to just see, like, if we put it on an illustration like this, to see like, oh, electrons are going to go here. But I think if you see it like this, it'll start to really click in your head. So the first one we're going to do, I'm just going to say this is an elemental semiconductor. We use silicon. So we have a bunch of silicon atoms there. Silicon's a group 4A. So each one of these silicon atoms is bringing 4 electrons to the table. And that's what I've drawn right here with these lines. And these different electrons, these will actually form bonds, right? So that's a bond right there. Those are bonded. Every atom is bonded using those electrons. So what do we do when we do an N-type semiconductor? Well, like I said, we're actually adding more electrons into the metal. So, for example, we can take a silicon and dope it with a phosphorus. Now, phosphorus is a group, it's a group 5A element. So, phosphorus is actually going to bring 5 valence electrons, while these silicons are only going to bring 4. So now I have an extra electron there in that phosphorus. Now, all these other bonds, they're all filled up, right? There's nowhere anything else can go because all the silicons are happy with each other. So the only place this electron can go is it's just going to get scattered around, right? It can hop around. It's not going to be happy there, so it's just going to keep hopping around. So that's the theory of an N-type semiconductor, is we add more electrons into the system, and there's no place for it to really go, so it's just going to bounce around everywhere. And that's how it can conduct electricity. Does anyone have any questions specifically on N-type semiconductors?
Is there like a point where you can add too many or something like that?
There was a question in class that was kind of brought up like that, and I think what you'll be tested on is typically a plus or minus 1 electron. I wouldn't take my word for that, but I know there was an example in class where he doped one that had adding 2 more electrons. And what Dr. Macedoni said was that it's just too unstable to do that. And so what I think is that he'll just do either plus or minus 1 electron from an elemental or compound, full octet. Okay, so moving on, let's talk about P-type semiconductors. P-type semiconductors are the exact opposite of N-types. What we can do is actually remove electrons from our metal, from our semiconductor, and then when you see that, we actually have empty space up here, unoccupied space, and so now these electrons can flow and conduct electricity. So if I say silicon, we added a group 5A element, now let's add a group 3A element that has 1 less electron, and we can use boron here. So boron only brings 3 valence electrons to the table, so I actually have a gap right here, right? So there's no electron right here because boron can only have 3. So this metal, this semiconductor, actually wants to make up for that deficiency. So what happens is, this electron can come hop right there, but then we have a gap right here. So then this one can come hop in right there, but then we have a gap right here. You guys see how that's going? Is that our electrons can flop places, but we're always going to have a gap somewhere. So our electrons are constantly flowing to make up for that gap, but it'll never fully be able to fill the octet again. And so that's how our P-type semiconductors work, is our electrons will flow because of that deficiency in electrons. And you can think of this deficiency in electrons right here like a positive charge. And we'll talk about that more in a second when we talk about how LEDs work. Does anyone have any questions on P-type or any of these types of doping impurities? Drew?
So the N-type and the P-type, they both have the ability to be conductive?
Yes, both are conductive.
But for different reasons. N-type is that they're adding electron, P-type is where they're losing an electron, having that gap.
Exactly. Yep.
So if you do both types of doping, so like phosphorus, like is that just like a compound semiconductor?
Yeah, so a compound semiconductor would have a full octet. It would be one 3A element and one 5A element. So in this example, I think what you're getting at is if I had a boron here and a phosphorus here,
Yeah.
I would have a perfect full octet of electrons for 8 in each for a total. So that would just be, it would come back to, that would just kind of be an intrinsic semiconductor. Yeah.
If you put a p-type or an n-type semiconductor into like a transistor or something that requires there to be a flow of electrons, would it still need a charge to make it flow? Or would it
Yeah, you would still need a charge to make it flow. And that's kind of how an LED works. That's what I'm going to talk about next. Yeah.
Is one better than the other and be,
No, they're equal. They're both going to conduct electricity. Yeah, Drew?
Intrinsic?
Intrinsic is just like your standard semiconductor, a full valence band and an empty conductive band. So a full octet, 8 electrons. Okay. Let's move on and do LEDs. So how an LED works is it basically uses these two different types of conductivity that we've talked about. Specifically a p-type and an n-type semiconductor. So what happens with an LED is we have these two different types of semiconductors basically sitting right next to each other. The way that I think about it is this gap right here in between is kind of just like a transition phase where your electrons can flow to the next type of semiconductor and then be dropped down. So what happens with an LED is we put a current through it, our electron flows come in this way, and we have an n-type and a p-type semiconductor. So in an n-type semiconductor, we have extra electrons in our conductive band. Now, right next to it, we also have a p-type semiconductor where we basically have positive charges in our conductive band. So what these electrons are going to want to do is if we have extra here and deficient here, these ones that we have extra of, they're going to want to drop down and feel these positive charges on the p-type semiconductor. So we put an electron flow through here, and these electrons are going to travel like this, kind of through the transition phase. And then as soon as they can, they're going to drop down and fill that deficient space, that positively charged electron. And you guys learned in Chem 105 that anytime an electron drops in energy, energy has to be emitted. And in this case, it's emitted as a photon. So every time one of these electrons drops, a photon is going to be released. And that is how we'll see LED lights. Depending on the energy gap and how far those electrons are falling, that will tell us what type of LED that is. So he could potentially, I'm just kind of making up a problem in my head, is he could give you, different energy gaps and say like, oh, which color might this be? And you'd have to, again, with the color wheel, know the relative energies. Yeah, Drew?
So the bigger the gap, the bigger the energy that's absorbed.
Would you know that, Brad? The larger the electron falls, the more energy it has when it leaves.
The more energy it produces.
Yeah. So the bigger the gap it falls, the more energy it has when it's released. So it'd be higher. A higher energy light would be released. Yeah.
Why do we need the electron flow to stimulate that LED? Why does the electron flow have to be there?
Because there's no other way to get them going this way, kind of, is that, like I said, this is kind of a transition phase, so if we push that electron flow that way, we can kind of force the electrons that way. Otherwise, if it was just this by itself, it would be fairly happy right there, just conducting, right? This would just be fairly happy, but if we push those electrons this way, then they start flowing this way towards the p-type, and then they'll want to drop down. Okay. Does anyone have any questions on these LEDs? Yeah.
Why don't the electrons fill up the p-type semiconductor and just make a normal intrinsic semiconductor? If you're just adding more electrons into
Into
that.
this? Because for every one that moves, you still have empty ones. So there's only one dropping at a time. So one electron will drop, but we still have, I'm sorry?
On the LED light for hours.
Because there's it's constantly flowing. So you think of this as an unlimited amount flowing this way, and only one electron's dropping at a time. So for if they were dropping right here, for example, we still have empty ones. So for every electron that drops, a photon's going to be released.
And maybe like if you ran it, actually, I mean, I don't know the answer to that question as well. Like, at what point does it just fill up all the way? Like, how I just keep running it? When does it just fill all the empty ones at one point? And that's a good question. I mean, I don't know if he talked about that. He didn't. So I think he wants to know like the mechanism to why it makes light. So it would be interesting to know if there's like a threshold, like after so much time, like you filled it. But I wonder then, like, would you be electron deficient above? So like at that point, yeah, I don't see. That's a good question. I think that would get into more of the physics that I don't think we talk about. I mean, it's a valid question, but I don't know.
Yeah.
What's the CB and BB again?
The CB is the conductive band, and that's the valence band.
Oh, right.
So valence band is your filled bonding orbitals. Conductive band is the empty antibonding orbitals. And these are all, like, this is just, I just tried to copy off the slides. All the pictures that we're drawing up here, we're basically just copying straight off the slides. So as you're studying for this test, as you guys have known, it's really like conceptual and factual. So I would definitely go over the slides again and make sure you know everything on there because it's actually really clear on the slides. So, yeah. Anything else right here before I pass it to Braden? Okay.
All right. So now we're getting into some like really factual stuff. We're going to go over the types of metals. You guys probably know this if you've already studied. And just like little simple facts about them. And maybe like the important little fact to know if you had to answer some sort of conceptual question, like a question that would be like, which is more likely to break? What is more brittle? Things like that. Right? So we have these different types of metallic, ionic, covalent, and molecular solids. So out of these, which one do you guys think is the easiest one to remember? There's two I think are the easiest because we kind of go over this type of thing in 105. Ionic and covalent, right? Hopefully that was your answer. So ionic and covalent of the four are probably the easiest to just like remember because you know the conceptual understanding of what is an ion and what is an ionic compound and you know what is a covalent bond. So, and then metallic and molecular takes a little bit more maybe just like reading or a couple explanations to just get it. But once you do, they're all really straightforward. So a metallic bond is just a bond between these metals. So that's a lot like just iron, right? Like pure iron, or like the electron C model that we were talking about, or the molecular orbital model. So we get these different types of metals, right? We're not mixing the different types because that's a what? If I mix metals, that's an alloy, right? We're not doing that. We have a pure substance. And what are some characteristics of metals that you guys know?
Malleable.
They're malleable, and what does that mean?
It means when you bend them, they kind of just slide around each other.
Yep, when we bend them, they just slide around each other. That's a good explanation. And also they're conductive, like what Corbin was just saying, so we can conduct electricity through these pure substances as well, through that electron C model that explains that. So that is metallic, a pure metal, right? Bonded to itself, it is malleable, so I can bend it and work with it and change its shape, and it also conducts electricity. So that is that, and I'll just write like iron, or this, those are examples. So now ionic. Ionic solids. Who can give me an example of an ionic solid, ionic compound? Someone say it loud. Sodium chloride, NaCl, perfect. So table salt, right? So that's a solid when we see it in our salt shaker, right? It's a solid. What are some characteristics of an ionic compound, an ionic solid? It's brittle, right? That's probably the most important one, right? It's brittle. They're not very strong. And you know that from the ionic compounds that you have in your home, like salt, like grains of salt, things like that. They're not strong bonds, right? Ionic bonds we know are not strong. So, first of all, I know that for ionic solid to exist, it has to be a metal bonded with a what? A non-metal, right? So if you were given a couple species and asked to classify them, this should be pretty straightforward stuff. If it's just iron, or if it's just the metal, then you know it's metallic, right? And they're in the metal area. But if it's a metal bonded with a non-metal, like clearly sodium chloride here, and you know it's an ionic, okay? That's an ionic solid, and it's probably more brittle, it's not as strong. What about covalent, right? What is the property of a covalent type of metal?
Hard.
it can be very hard. What's a good example of that? A diamond, right? So very hard, right? It can be very hard, and we have a diamond. So not all of them are, right? We're not saying everyone is, but most of them are, right? They are pretty strong. So that would be some type of non-metal bonded with itself, right? Like pure carbon, right? And carbon, we can either get the diamond form or the graphite form. And depending on the lattice structure and how they're bonded together, they're either really strong, we get this cool diamond, or we just get graphite. So it's really interesting how the structure of how the elements, how that atom is bonded to other atoms really affects kind of the value and what we can use it for. So that's really cool.
What about a compound that is a metal, well, not a metal,
A non-metal?
a non-metal that's bonded to a different non-metal?
A non-metal bonded to a different non-metal. If it's a solid, I would still call it a covalent solid, right? Because it would just be a covalent bond of sharing electrons. So, which brings up a good point. If that was confusing at all, when we're classifying these, look at the type of bond and then determine what it is, right? So don't say, oh, it's carbon with nitrogen, but if it's a solid of some type, then it's still a covalent solid. That's why it's not all of them are really hard, but it can be hard. So the characteristic that's really crucial or important is the fact that covalent ones can be very hard and ionic ones are always brittle. Okay? So what about molecular? This one's a little bit more difficult to understand, kind of. The name kind of gives it away, but what's like an example of a molecular solid? Ice? Did you say ice? Okay. Ice, so is water. Why does ice classify as a molecular solid? Who can say? Yeah?
We're not actually forming covalent or ionic bonds with it. It's just intermolecular forces that are holding that together.
Perfect. That's a great explanation, right? So we're not actually forming some type of solid with our bonds. We're not forming an ionic compound, right? We're just one of those bonds that is the solid, right? But rather we're forming a molecule, and the molecule as a whole exists in several phases depending on which temperature I'm at. And if I give it the right energy or take the right energy away from it, right, I can form these intermolecular interactions. So not atom to atom, but molecule to molecule, like hydrogen bonding within water to form solid ice at 0 degrees Celsius. So things like that, right? So if you're given a problem where you're given a molecule, it talks about the fact that it can hydrogen bond and it's a solid, what type of solid it is it? It's definitely molecular, okay? So if it's molecule interacting with another molecule, molecular. If it's atom with atom that seems to form a structure, like a lattice type structure, then that's definitely going to be either of these, right? And if it's ionic bonding going on, metal, non-metal is ionic. If it's two non-metals together, it's covalent, and if it's just metals alone, then it's metallic. Okay, so that's it with understanding bonding. Go ahead, Jim.
Are the molecular bonds very weak, and are they weaker than the ionic?
Yeah, they're weaker than the ionic even.
So
In terms of just, because there are certain exceptions, but let's rather go off the rules. You guys remember in Chem 105 doing like different types of intermolecular interactions, and we had ion to ion dipole, and dipole, right? That's when we're getting into that helps us also understand the strengths of these. So we would definitely say probably this is the hardest, and then maybe something like this, and then probably ionic, and then in some cases, right, we get fairly hard molecular ones, but they're usually the softest ones. So you would want to consider this one your weakest solid. Because it is an intermolecular interaction, like a hydrogen bond, or even London dispersion forces under certain temperatures can give me a solid. Okay. Would you mind just throwing this thing up? So the next thing let's talk about is alloys. So we mentioned it, right? What makes up an alloy? Someone say. It's a mixture of metals. So we mix two different types of metals together to form something. Now, is that good? Yeah, it depends, right? That can be really good. What does it generally do for us to make an alloy?
makes the metal stronger.
It makes the metal stronger. That's generally what we're doing with an alloy. We're changing its chemical property to increase how strong it is. So there's several types here, right? We have alloys, we have substitutional, intermetallic, and we have interstitial here. So let's first talk about a substitutional alloy. So who can explain to me what a substitutional alloy means? Yeah.
When you have a metal, then you replace
was with another metal.
right? So you replace some of the items with another metal, and there's like a really specific thing. It's very important. Like if you guys are sleeping, this is like wake up right now because you probably have a question on this. What? Do you know what the specific thing that makes it substitutional? Has to do with the radius. Does anyone remember? Right here.
That's
In the front,
like
loud.
15%.
It has to be within 15%. The radius has to be within 15% of one another. So that is because if not, right, if you're really small compared to the other ones, what usually happens? You fall into the cracks and form an interstitial right here. So it's replacing a metal with another, but our radius have to be within 15% of one another, right, in terms of size. So just know that it's not going to be substitutional unless the radii are that close to one another. So you do not have to usually look at the periodic table and say, oh, I know the exact amount of that radius. But if I remember right, it's given to you. It's given to you what the radius is of different atoms. And you predict whether or not they could do substitution or not, depending on the ratio of being 15% of, in terms of how close they are to one another.
So I don't know if you said it yet, but if the radius is smaller, then it becomes interstitial, right?
If it's smaller, yep, if it's smaller, then it becomes interstitial. So what happens here, this is good, right? We can increase the strength, we can give it some different type of property that might come from one of the other elements and one of the other sides, as long as it's close to the same size, and make it stronger or change the property that we want to happen. But we know we're making it stronger when we do this interstitial, because what's happening is we're taking these larger atoms that are